Thorium. Thorium in nuclear energy. Introduction. The strategic significance of thorium. Thorium has emerged as one of the most strategically significant alternative nuclear fuels in the 21st century, representing a potential structural shift in the global energy architecture. Unlike conventional uranium based nuclear systems, thorium introduces a fundamentally different fuel cycle that promises enhanced fuel efficiency and reduced long life radioactive waste, and potentially greater resistance to nuclear proliferation. The growing interest in thorium based energy system is driven by increasing global energy demand, geopolitical volatility in fossil fuel markets, climate change mitigation pressures, and the limitations of existing nuclear technologies. The thorium fuel cycle is frequently positioned as a fourth generation nuclear technology capable of redefining the technological frontier of energy production. Thorium itself is not fissile, meaning it cannot directly sustain a nuclear chain reaction in its natural form. However, thorium 232 is fertile, meaning it can absorb a neutron and transmute it into uranium 233, a fissile material capable of sustaining nuclear fission. This breeding process introduces a highly efficient nuclear fuel cycle that theoretically allows for more complex utilization of nuclear fuel compared to conventional uranium reactors, which typically use less than 5% of the potential energy contained within mined uranium resources. The result is a fuel system with potentially orders of magnitude greater energy extraction efficiency. Historical development of thorium-based nuclear concepts. The theoretical foundation of thorium-based nuclear energy dates back to earliest years of nuclear research in the mid 20th century. During the 1950s and 1960s, significant experimentation with thorium fuel cycles was conducted, particularly within the United States under the molten salt reactor experiment at Oak Ridge National Laboratory. Despite promising technical results, geopolitical pressure, military priorities, and the strategic value of plutonium production shifted nuclear development towards plutonium, uranium-plutonium fuel cycles, which were more aligned with Cold War weapons program. Thorium research didn't disappear entirely, but investment levels declined significantly. After the 1970s, renewed interest began to re-emerge in the late 20th century as concerns regarding nuclear waste, safety, and uranium resource scarcity intensified. Countries with large thorium reserves, particularly India, China, and Norway, began reconsidering thorium as a past of long-term as a path of long-term energy as a long as a part of long-term national energy strategies. India's nuclear roadmap, for example, explicitly incorporates thorium utilization as a central pillar due to country's limited uranium resources, but abundant thorium deposits in monazite sands. Modern uranium research has accelerated due to advances in computational modeling, material sciences, and reactor engineering. One recent technological milestone involved experimental demonstration of thorium conversion within a molten salt reactor system, indicating measurable progress in operational feasibility. Nuclear physics of thorium fuel cycles. The thorium fuel cycle is built upon neutron absorption and nuclear transmutation process that convert thorium 232 into uranium 233 through intermediate decay stages involving protactinium 233. Uranium 233 possesses nuclear characteristics that make it highly efficient for sustaining chain reactions with neuron favorable neutron economy compared to uranium 235 or plutonium 239. The neutron economy refers to the balance between neutron produced and neurons absorbed within the nuclear reactor system, which determines the sustainability of chain reaction and the efficiency of fuel breeding. Thorium reactors are often conceptualized as breeder reactors, often because they generate more fissile material than they consume. The conversion ratio, a measure of how effective fertile material is converted into fissile fuel, plays a critical role in determining long-term sustainability of the fuel cycle. Higher conversion rates and ratios imply greater fuel independence and reduced dependence on enriched uranium supplies. The nuclear characteristics of thorium contribute to reduce production of transuranic elements such as neptunium, americium, and curium, which are major contributors to long-term radio toxicity in conventional nuclear waste streams. Consequently, thorium-based waste profiles are often considered easier to manage from a geological storage perspective. Reactor designs compatible with thorium utilization. Several reactor architectures are compatible with thorium fuel cycles, including molten salt reactors, heavy water reactors, high temperature gas cooled reactors, and fast breeder reactors. Among these, molten salt reactors are frequently considered the most promising due to their ability to incorporate liquid fuel, enabling continuous removal of fissile materials and online refueling processes. Molten salt reactors operate using liquid fluoride or chloride salts, both as coolant and fuel carrier. The liquid nature of the fuel allows for more stable temperature control, reduced pressure requirements, and inherent safety characteristics derived from passive cooling mechanisms. Because molten salt reactors operate at atmospheric pressure, the probability of explosive pressure driven accidents is reduced relative to conventional pressure water reactors. Recent experimental developments demonstrate ongoing technological progress in molten salt reaction technologies, while circulating fuel systems. High temperature gas cooled reactors represent another promising pathway for thorium utilization, particularly in industrial heat applications such as hydrogen production and synthetic fuel generation. The combination of high outlet temperatures and efficient neutron economy creates opportunities for integrating nuclear energy into broader decarbonization strategies beyond electricity generation. Resource abundance and global thorium distribution. Thorium is significantly more abundant in Earth's crust than uranium, with estimated reserves approximately 3 to 4 times larger than known uranium resources. Major thorium deposits are located in India, Australia, the United States, Brazil, Norway, and several African countries. Monazite sands, a primary source of thorium, are commonly found in coastal regions where heavy mineral deposits accumulate through geological processes. The geographical distribution of thorium resources introduces a potential strategic advantage for countries seeking energy independence. Nations lacking uranium resources may still possess Nations lacking uranium resource may still possess significant thorium reserves, allowing for diversification of nuclear fuel supply chains. Reduced reliance on uranium enrichment infrastructure could alter the geopolitical landscape of nuclear energy by decreasing dependence on a limited number of enrichment capable states. Thorium's relative abundance implies a long term fuel supply capable of supporting global electricity demand for several centuries, assuming continued improvement in reactors efficiency and fuel recycle technologies. Safety characteristics of thorium based systems. Safety considerations represent one of the central arguments in favor of thorium reactors deployment. Thorium based molten salt reactors often incorporate passive safety mechanisms that rely on physical laws rather than active mechanical interventions. For example, many molten salt reactor designs include freeze plugs composed of solidified salt maintained by active cooling systems. In the event of power loss, the plug melts, allowing liquid fuel to drain into passively cooled storage tanks where nuclear reaction cease. Thorium fuel cycles also produce lower quantities of long-lived transuranic isotopes, potentially simplifying waste management challenges. Although thorium reactors still produce radioactive waste requiring containment, the radiotoxicity profile is often characterized by shorter half-lives compared to conventional uranium plutonium waste streams. Lower operational pressure reduce the risk of catastrophic coolant loss accidents, and the thermal properties of molten salt enables efficient heat dissipation. These characteristics contribute to the perception that thorium based systems could offer improved safety margins relative to traditional nuclear technologies. Waste profile and environmental considerations. One of the most frequently cited advantages of thorium based nuclear energy is the potential reduction in long lived radioactive waste. Conventional uranium reactors produce plutonium and other actinides with half-life spanning tens of thousands of years. Thorium reactors, by contrast, tend to produce waste dominated by fissile products with shorter half-lives, reducing the duration of required geological storage. However, waste management challenges are not entirely eliminated. Uranium 233 production can result in trace contamination with uranium 232, whose decay change emits strong gamma radiation, complicating fuel handling and reprocessing operations. These technical challenges require specialized remote handling technologies and robust shielding procedures. Environmental considerations extend beyond waste management. Nuclear energy systems, including thorium reactors, produce minimal greenhouse gas emissions during operations. Life cycle emissions include mining, fuel processing, construction, remain significantly lower than fossil fuel alternative. Consequently, thorium-based nuclear energy is frequently discussed as a component of long-term decarbonization strategies. Economic feasibility, technological barriers. Despite theoretical advantages, thorium-based nuclear systems face substantial economic and technological barriers. The nuclear industry exhibits strong path dependence, meaning existing infrastructure, regulatory frameworks, and supply chains are optimized for uranium fuel cycles. Transitioning to thorium requires significant capital investment in research, development, licensing, and demonstration projects. Reactor construction costs remain high relative to other energy sources, particularly renewable sources such as solar and wind. The economic competitiveness of thorium reactors depend on technological maturation, regulatory acceptance, and economies of scale. Initial deployment phases are likely to involve higher risk due to limited industrial experience and lack of standardized designs. Fuel reprocessing technologies necessary for closed thorium fuel cycles require further development to achieve commercially viable technologies. The chemical complexity of separating uranium 233 from irradiated thorium introduces additional engineering challenges that must be resolved before large scale deployment becomes feasible. Geopolitical implications of thorium adoption. Thorium based nuclear energy has potential geopolitical implications that extend beyond energy markets. Countries possessing and processing large thorium reserves may gain strategic leverage in global energy supply chains. Reduced dependence on uranium enrichment could weaken the influence of states currently dominating nuclear fuel markets. Proliferation resistance is often cited as an advantage of thorium fuel cycles because uranium 233 produced from thorium is typically contained with uranium 232, whose strong gamma radiation complicates weapons handling. While not entirely proliferation proof, thorium fuel cycles introduce additional technical barriers that may reduce incentive for weapons deployment and development. Technological leadership in advanced reactor designs may also confer strategic advantages similar to those associated with aerospace, semiconductor, and artificial intelligence industries. Nations investing heavily in thorium reactor development may gain influence in future energy governance frameworks, future prospects, and research trajectories. Research into thorium based nuclear energy continues to expand as governments and private firms explore next generation reactor concepts. Demonstration projects remain critical for validating engineering assumptions, cost projection, and regulatory frameworks. Progress in material science, corrosion resistance, and fuel chemistry will significantly influence the pace of technological adoption. Several long term scenarios envision hybrid energy systems in integrating nuclear, renewable, and storage technologies to create resilient, low carbon grids. Thorium reactions, thorium reactors could play a complementary role in providing baseload electricity, while intermittent renewable sources contribute variable generation capacity. The trajectory of thorium adoption will depend on political will, investment flows, and public perception of nuclear risk. Technological breakthroughs in nuclear modularization, cost reduction, and fuel cycle optimization could accelerate adoption cycle timelines. Conclusion. Thorium, thorium nuclear energy represents are technologically plausible but institutionally constrained pathways towards long term energy security and decarbonization. Its advantages in fuel abundance, waste profile, and safety characteristics position it as a potentially transformative energy source. However, Structural barriers related to cost, infrastructure inertia, and regulatory complexity limit near term adoption. The long term strategic value of thorium lies in its capacity to extend the technological frontier of nuclear energy based beyond the limitations of uranium based systems. Continued experimental validation, demons- demonstration projects, and interdisciplinary research will determine whether thorium transitions from theoretical promise to an industrial reality.